Suppose you have two flat glass plates and one edge is connected together. On the other edge, you put a very fine wire with a circular cross section. It could be hair, or it could be anything like a paper. And then you illuminate this from above with the monochromatic light, let's say with the wavelength of 600 nanometers. And you will see a series of bright and dark bands on the top glass. This pattern is developed like very similar to the thin film interference. In fact, this is a thin film interference. It's a thin air film. So the wire creates this little thin layer of air between these two flat glasses. So therefore, we have to take approach to this problem from a point of view of a thin film interference. Before we do that, let's see what's given to me to us. As I mentioned earlier, our wavelength was 600 nanometers. And let's suppose that there are 30 dark fringes that are formed. And we want to find out what is the diameter of the wire. So the diameter will be this part right here of the wire, pretty much the thickness, at that point. As we're going to solve this problem with the thin film interference approach, which is actually a thin film in reality, but thin air film. So then we need to consider two effects. First is the path difference, and the second is the phase shifts. To analyze these two, I drew this diagram where incident ray to the glass surface and then to the air wedge produces two reflected rays, 1 and 2, reflected ones that will interfere and create this interference pattern. Now, to identify the condition for the dark fringes or destructive interference, we need to identify the phase shifts and the path length. So we have two spots, 2 points, one here, let's call it point A, and another one here, point B, where the reflection in reality happens. So these other 2 points, here, and here, are transmitted rays. We don't consider phase changes. Now let's go back to the point A. At point A, what we have an N glass. It goes from a higher index of refraction to N air, which is lower index of refraction, so no phase shift. For point B, now it goes from N air, which is less than N glass, which means there is a phase shift of 1/2 lambda phase shift. Now the path difference would be the extra distance that the second ray goes from A to B and B to, let's call it C here, AB plus BC, but each of these could be approximated to the T. It's 2 times the thickness. Now, if I want to write the condition of destructive interference, then I have to say that consider the distance difference, path difference, and the phase shift. So path difference is 2t plus 1/2 lambda phase shift. should equal, for destructive interference, we have 1m plus 1/2 lambda. Okay, so if we simplify this equation, we will get 2t equals m lambda. So here we understand that the thickness is the same as the diameter of our wire. So in reality, the diameter could be equal m lambda over 2. Now we know what's the lambda. How about the m? Well, don't rush to say 30 because there are 30 dark fringes. So the first dark fringe actually occurs at the end where the plates meet, right here. Let me just show it to you. Dark fringe happens at this point, first one. And the destructive interference occurs because of the phase reversal caused by the light reflecting from the top of the lower glass slide. For 30 dark fringes, including the one where the plates meet, m should equal 29. So m should equal 29 for the 30 dark fringes. Take a moment to think about this. Now we can in fact plug in the numbers and solve for d. So then d equals 29 times 600 nanometers. I don't even bother to convert this because my answer could be in nanometers or even less. And punch this into a calculator, you'll get 8.70 times 10 to the negative 6 meters, which is 8.7 micrometers. It's like a hair-like wire. Thanks for watching. Stay tuned for more.